This project aims to explore the biomechanical implications of aortic valve stenosis by presenting a simplified model of bicuspid and tricuspid valvular bending in both healthy and diseased states. Aortic valve stenosis is characterized by a thickening of the aortic valve leaflets and a narrowing of the valve itself. Two primary causes of stenosis include having a bicuspid instead of a tricuspid valve and calcification. The disease can lead to complications such as heart failure, stroke, blood clots and bleeding, arrhythmias, endocarditis, and even death. Current research aims to model aging of the aortic valve by implementing a simple growth law of calcium nodule progression. One approach includes implementing a radial expansion model. However, this approach presented a simplified analysis of aortic valve stenosis to provide a basic understanding of the biomechanical effects of the disease.
We modeled our aortic valve leaflet to be a Lehigh material, and we assumed that the curvature of the aortic wall was insignificant, such that the leaflet is triangular. We also approximate the load on the leaflet due to blood pressure and contact with other leaflets to be linear across its length, and that the right end of the leaflet is attached to the arterial wall and fixed. We modeled pure bending using the shear force and moment equations derived in class, and solved for the bending moment using boundary conditions at the free end. Then, using the aforementioned bending moment and the fixed end boundary conditions, we solve for the deflection profile as a function of x.
Our model for the calcified leaflet is similar to that of the healthy leaflet, only with a uniformly increased thickness across the body of the valve. Assuming the calcification layer does not change the Young's modulus, because the only difference between the two models is thickness, it follows that the form of the displacement function solution must be the same. We make the assumption that in order to maintain adequate blood flow through the aorta, the displacements of both models must be equal. Based on this, we can demonstrate that the force of flow must increase to accommodate a thicker valve. This explains the increase in blood pressure in ventricular hypertrophy commonly observed in stenosis patients.
We also examined the effects of bicuspid congenital defects on ventricular pressure. We approximate the valve width as the arc length of the circle and compare the deflections to find the relationship between bicuspid and tricuspid ventricular pressures. In summary, we found that calcification thickens the aortic valve, which leads to higher ventricular pressures. Bicuspid geometry also lends itself to higher ventricular pressures. Although our approximations are fairly inaccurate, our results are consistent with observed symptoms. Thanks for watching.